Hello students, I am Olabisi Olawoye. I am your chemistry tutor, and on this platform I'll be revising chemistry questions with you using the WAEC syllabus. This is brought to you by Ighota Virtual Learning Platform. I will advise you to stay tuned and pay attention. Be meticulous about everything we are doing here, because this topic is well prepared based on the WAEC syllabus. Now, the topic I'm going to start with today is the measurement, scientific measurement. And under scientific measurement, I'm going to be teaching you the importance of scientific measurement, the meaning, and those physical quantities that are being measured in chemistry. Their units, that is their SI units, the derived unit as well, the differences between the fundamental or basic unit and the derived unit. Then we also learn the other aspect of this topic, which is the difference between precision and accuracy. We will also learn the importance of significant figures in taking readings. And I want you to watch out for the second part of this topic, which is on scientific method. Now, the first part here is the scientific measurement. What is the meaning of a scientific measurement? A scientific measurement is actually a measurement that is taken to concisely and clearly convey an observed value. That is, when we take measurement, we want to know the value of the measurement we are taking. Now, we use common scientific tools like meter rules, scales, and graduated cylinders. That is, cylinders that have numbers written on their body. Now, what's the importance of scientific measurement? The essence of scientific measurement is to get a precise and reliable result, because when we take measurements, we'll be able to deduce or get other points from the measurement we are taking. And as a science student, especially in chemistry, you'll be carrying out different practicals, like in qualitative analysis, quantitative analysis as well. So it is very important to know how to take readings and to convert one readings to another, or one unit to another. And science also depends on repeated experiments to confirm findings. So it is important that during this measurement, we repeat our experiments to confirm our findings and to get our reports in a clear and concise measurement. Now let's look at the physical quantities and their measurement. What are the various physical quantities that are measured, and their the materials that are used to measure them? Examples of such are length, which is the distance between one point and the other point. We can get the length of a book, the length of a table, the length of a particular distance. Mass is also another physical quantity, and which is the quantity of matter in a body. The temperature, which is the degree of hotness or coldness of a body. Yes, we can say the body is hot, the body is cold, but we really need to know how, to the extent at which the body is hot. So we need to take values or readings, or assign readings to all these parameters or physical quantities. Other examples are current, amount of substances, time, and luminous intensity. All these points that are mentioned, that all these physical quantities are known as basic quantity or fundamental quantities, and units of measurement are actually assigned to them. What is a unit of measurement made up of? It's made up of the collection of standard and other units that are used to measure various physical quantities. Now, we have, in the early days, we didn't have any proper tools to measure the physical quantities. We only use some body parts, that is some informal methods and unit of measurement. For example, in the olden days we use, in the early days we use body parts such as hand span, foot span, arm span, cubit, pace, that's the pace of our hands. We use it to take measurement. But since the body parts varies from one person to another, these methods of measurements does not give an accurate result. So gradually better units of measurements were invented. And so these new units are called the metric units. And they have the SI unit assigned to them, which is an international system of units. And there are 7 basic or fundamental units altogether based on the physical quantities. Now, these physical quantities like mass has the unit or fundamental unit, which is kilogram. The abbreviation is kg. Length is meter. The abbreviation is m. Time is second. The abbreviation is s. Amount of mole is another one. The abbreviation is mole. Electric current is another one. The abbreviation is ampere, which is A. We have luminosity, and the unit is candela, CD. Temperature, the unit is Kelvin, which is K. So other units have also been derived from these 7 fundamental or basic units. Those units are called derived units. We get them from the fundamental units. Now, for instance, now, if you want to measure length, we no longer use only kilometer. You know that length actually here, when we check the fundamental units, it is derived from the basic unit of length is meter, and the abbreviation is m. But kilometer was also derived later. Meter, centimeter, millimeter. And what's the relationship between all this? Kilometer, for instance, now contains 1,000 meter, while meter and centimeter, 100 meters make 100 centimeter makes 1 meter. So if you have 200 centimeter, it is 2 meter. But kilometer here is 1,000 meter. It contains 1,000 meters. So 2,000 meter is 2 kilometers. And kilogram, gram, and milligram, they also have this relationship. Actually, the mass, the unit of mass is kilogram. But other ones like gram, milligram were coined from the mass. So for instance, now if you are dealing with a calculation and you're expected to express your answer in gram, for instance, maybe you are calculating the force of a body, which is mass times acceleration. The force must be in kilogram. So, and if you are given your question in gram, for instance, you are given 500 gram, you need to divide it by 1,000 to get it in kilogram. So you should understand the conversion of all these parameters. Another one is capacity. Let's take, for instance, now, I'm going to use mass as an example. Mass, assuming you are working with a mass of 500 gram, and you are expected to convert it to kilogram before you use it in your calculation. What will you do? The fundamental unit of mass is kilogram. To convert it to kilogram, now, to convert this 500 gram to kilogram, we need to divide by 1,000 gram. So our answer here is 1/2, which is 0.5, because 2 will go in 1 as 0. 2 is not dividing 1, so we write 0. Multiply this 1 by 10. 2 in 10, that is 5. 0.5 kilogram or half kilogram. So this is a very important or crucial aspect in science. You must be able to convert. Now, capacity is also the volume here. We have kiloliter, liter. We have milliliter. The same relationship occurs here. Another one is time. we have time here. The fundamental unit is second, but other units were derived from second. And they are minutes, hours, second, days, week, month, year. Now, another example is temperature. The fundamental unit here is Kelvin, but it was later, other units were discovered or derived from Kelvin, and that's Celsius, Fahrenheit. So temperature can also be measured in Celsius and Fahrenheit. Now, looking at that, we will quickly consider those examples of derived units. I'm going to give you the meaning first. What's the meaning of derived unit? All other units that are derived from the 7 base units or fundamental units are called the derived units. A very good example here is the density. What is the formula for calculating density? Mass per volume, or mass over volume. Knowing fully well that mass is in kilogram and volume is in centimeter cube. So using this, or let's say volume is in liters. Now, but when it comes to liquid, 1,000 centimeter cube is also 1 liter, and which is 1 decimeter, 1 dm cube. Now, looking at this now, so it means that volume can also be represented as centimeter cube. So 2,000 centimeter cube is 2 dm cube, and that is 2 liters. So here now we have kilogram per centimeter cube, which is the density, which is the volume, the unit for density. So we can see here that density is not part of the fundamental unit, whereas it was derived from the fundamental unit, and the unit is kilogram per cm cube. We have other examples. Take for instance, power. Power is equal to work done over time taken. Now, it should be noted that time taken is second, work done is in joules. Work done is a form of energy, and energy is measured in joule. So the unit of power is joule per second, joule over second, or watts. All these are derived units. We have other examples like, for instance, molar concentration, which you are going to use in your titration. Molar concentration, which is known as mole per dm cube, is equal to mass concentration over molar mass. And the mass concentration is gram per dm cube, whereas molar mass is gram per mole. Now, looking at this, if you cut this gram and gram, what we have here is mole per dm cube. You can see the reason why molar concentration is mole per dm cube, and is also a derived unit. Now, the SI base units and derived units are not even always useful. So some prefixes have been coined out. You will see things like kilogram, grams, centimeters, Newton, watts. These are the commonly used units nowadays. So under that, we will also consider precision and accuracy in measurement. Having known the unit assigned to different physical quantities in order to avoid confusion. For instance, you are measuring distance it should be in meter or centimeter. Your measuring time is in second, or hour, or minutes. So the essence of assigning units to physical quantities is to avoid confusion and to get a precise value and concise value. So under that, we are looking at precision and accuracy. What's the difference between precision and accuracy? Because it is actually used interchangeably. The word accuracy is a measure of how close your measurements of a quantity are to the true or accepted value of that quantity. Now, your precision measures how closely repeated measurements agree with each other. Take for instance now, you are to titrate. Maybe during titration, the volume of acid and base, that the volume of acid that neutralizes a base is roughly 25 cm cube. Now you carried out another test, another experiment, and you got 24.90. Another one was repeated, you got 24.80. It is clearly shown in these readings that though 25.00 is the accurate value or accepted value of the quantity, but to be precise, you need to repeat your titrations. So when those values you get, when they are in concordance and there is a difference of just 0.1, 0.2, you will be sure that your readings are correct, and you can find their average to get the precise value. So from here, we look at another example. Take for instance, you wanted to use a ruler to measure the length of a pencil. Now look at a ruler that is well calibrated or graduated, and then look at another ruler that has estimated values. Now this is the pencil in between. If you are to measure this pencil on the ruler here, taking a close look, in between 1 and 2, we have 1.1, 0.2, 0.3, 0.4, 0.5, 0.6, like that. Now, but looking at the second ruler, you just have 1, 2, 3, 4. So if you compare it here, you will see that you get 8 centimeter. It is easily assumed here that the length of the pencil is 8 centimeter. Whereas if you are to consider this part, you get 7.9 centimeter. Now it means that the 7 is certain, but the 0.9 is not certain. Now you can see here that the second ruler gave us an accurate value, whereas the first ruler gave us the precise value. The second ruler only gave us an approximated value, but we are not accurate. We are not precise. We are not precise. It's actually accurate but not precise. So it is possible to be accurate and not precise, or precise and not accurate. Now, I'm going to use another example, which is very important under significant figures. If you are taking readings in pipettes, the pipette and burette, during titration, let's assume this is the burette, which is usually 50 cm cube, and it contains the acid. Now, if you have used, or you fill this pipette up, the burette up to the brim, and then you titrate, after titrating, then the whole acid was used up and it ended here. Now you can see this sign that this is like a curve. When you are looking at a liquid in a glass apparatus, it will be in form of curve. So we have this is called the lower meniscus. This is a meniscus, and then you trace the line here wherever it ends. Now let's assume that you have 10, 20, 30, and there are no readings in between. You will not get the precise value. But if you have 0.1, 0.2, 0.3, 0.4, your readings will be accurate. So don't forget, when you are taking readings in titration, we look at the lower meniscus. You look at the solution where it ended, it will look like a curve. Then you take the readings underneath, not up. Now, in titration as well, it is very important to record your values to 2 decimal places. The reason is to get an accurate value or a precise value. But if we titrate and then we get 20, you write 20 instead of 20.1, or you write 25 instead of 25.3, 24.20, you write 24.5, or 25 instead of 24.80. You will see here that by the time you are repeating the titration, you end up getting the same approximated value. But if you take readings, you take to the readings, and as it is, as the burette is calibrated, you take a close look at the burette. Using this ruler as an example now, let's assume this is a burette. If your readings stop here, this is accurate. But if it ends here, you need to take the readings carefully, and you will realize that your answer will not be in a whole number. It will be in decimal places. So the essence of writing our answers in significant figures at times is to get a precise value and to get a better result and better analysis. Because from our figures in sciences, we analyze our results to get recommendations and conclusions. So it is very important as a scientist or as a science student to take a close look at your readings, and this explains the importance of significant figures in measurement. The significant figures, the number of significant figures in a measurement is equal to the number of certain digits and ones on certain digits. Take for instance, you have 2.80. There are 2 significant figures here. Now, if your value is just 2.0 or 3.0, here 3 is certain, 2 is certain as well here, but this 8 is not certain. If you round it up to 3.0, it means you have just rounded up your values. But if you have 2.80, this is showing that the result is precise. So we can say here that the greater the number of significant figures, if you now have 2.88, this is even getting to a higher level of accuracy and preciseness. Now, the greater the significant figure, like here we have 3 significant figures, here we have 2. Now, the greater the number of significant figures, the lower the degree of uncertainty. It means that our certainty is sure, is like 90%. So the greater the number of significant figures, the more precise our measurements are. So when we take a close look at details, even the little details, we are becoming more precise, and that is necessary in sciences, especially in titrations, where you will need to get your values in concordance. Values that are in concordance are usually recorded, and then in titration, the average of such values will be calculated, and then it will be compared with your teacher's result. Watch out for more of these teachings and recordings under titration, how to write tables of readings in titration, as we revise together under this series. I want you to be serious and treat past questions. Expose yourself to past questions as the day draws near, because it will help you so that you will not end up practicing in the exam hall. Now, we are going to look at some questions here. The first one here: why is it necessary to take readings in titration to 2 decimal places? The second question: why is titration readings repeated in quantitative analysis? What is the concentration in gram per dm cube of a compound weighing 50 gram in 250 cm cube water? And lastly, we are to convert the following: I'll give you some time to check this because these are WAEC question under practical. These two questions came out under practicals, and then this one you can't do without it under titration calculation. So, but this one you come across it in a day-to-day activities and in day-to-day calculations in other aspects of chemistry. So I'll come back. I'll give you time to solve these questions, after which we'll solve them together. Welcome back to the WAEC past questions revisions on measurement. I believe you've taken time to solve these questions. And if you're having any issues, you can always get back to me through the comment section. Let me know or hear you out wherever you're having any challenges. And I want you to note that this is a continuous practice. When we are done, after this topic, we move to the next one. It's a series of topics, which is a scientific method. And then we still move to other calculation questions as well. So please, I would advise you to follow this series. Now, the first question here is, why is it necessary to take readings in titration to 2 decimal places? In titration, it is necessary to take readings to 2 decimal places so as to get a precise value. Because in your titration, let's assume the titer value of your teacher is 24.00. Now, the bull rate is in this form. Now, looking at the bull rate, let's assume this is 1 and this ends at 50, 10, 20, 30, 40, and so on. So, in between these values, you have other readings. Or let's assume this is 1, 2, 3, 4, 5, 6, up to 50. Now, we have 1.1, 1.2, 1.3, like that, up to 9 lines in between to the next one. So, when you are taking your readings, it is very, very possible that the reading may not be exactly on 2. So, when you are taking readings here, we are dealing with volume. The volume, the exact volume, which can be to 2 decimal or 3 decimal places, so as to get a precise value. So it is very, very possible that the chances that we get answers to 1 decimal place is very, very sure, and is very, very high. And that's why even when we are writing 24.1, we write as 21.10, but there's nothing like 24.15, 24.16 in taking bull rate readings, though we can get that when we calculate the average. Let's assume maybe you repeated your experiment and then you got 23.90. Then another one gave you 23.70. Then you see have the fourth one, which is 23.80, or you got the same thing. It is from here you can see that there's a large difference, or a high difference between, wide difference between 24 and 23.80. So usually in titration, you are encouraged to use values that are in concordance, that is, values that have a difference of 0.1. So you can use any of these two that are very close, or 23.90, 23.80, 23.70, and 23.80. You can use this, calculate your average, and get your titer values, which is the average volume of acid used. So it is, this answer here is to get a precise or accurate readings. Why is titration readings repeated in quantitative analysis as well? Just like, why is it important to take our readings to 2 decimal places to get the precise volume? Here too is to get an accurate result, to get values that are close to each other, that are in concordant values. Values that are in concordance, that is, their difference is just 0.1, 0.2. That's why we repeat titration. We do rough readings first, before first titration, second titration, and third titration. Now, the third question, what is the concentration in gram per DMQ? Gram per DMQ, that's gram over DMQ, or gram in 1000 cm cube, 1000 centimeter cube, which is volume. dm cube. 1 dm cube is 1000 centimeter cube of a compound weighing 50 gram in 250 cm cube water. What we need here is just an excerpt from titration calculation, and you may be given your answer in this form. You may be given your question in this form. You need to convert first before you do your calculation. So if you are given 50 gram in 250 cm cube, you can't use it in calculation. You cannot use it as gram per dm cube, because this is gram per cm cube, and this is 50 gram in 250 gram, whereas the mass concentration unit is gram per dm cube, not cm cube. So you need to convert this to dm cube. If 50 gram is in 250 cm cube, 50 gram is in 250 cm cube, how many gram, that is x gram, will be in 1000 cm cube or 1 dm cube? So you cross multiply x times 250 equals to 50 multiplied by 1000. Dividing both sides by 250, you will get your answer. So this is 200 gram per dm cube, or 200 gram in 1000 cm cube. So this is the best way of doing it before you can use these values in your calculation. You have to convert the following: 2 hours 15 minutes to seconds. What do we use? How do we convert this? Please take notes. This is very, very common in electrolysis calculation, where, for instance, you want to get quantity of electricity, which is in coulombs, and it's current times time, and the time here must be in seconds. So if you are given time in form of hours and minutes, if you are not careful, you may miss out the answer. So you need to understand your conversion. You need to convert your 2 hours first. 2 hours, 60 minutes is inside 1 hour. That is 1 hour is made up of 60 minutes, and 1 minute is made up of 60 seconds. So to convert these 2 hours to seconds, you need to convert it to minutes first, which is 20 times 60 minutes. Then your answer here will be converted to second, which is 120 minutes multiplied by 60 seconds before you get your answer. And then you see I have 15 minutes here. So 15 minutes, you need to convert it to second by multiplying by 60. So working out our answer here, let's quickly work out our answer. 15, 60. This is 30, 6, 9. So this alone is 900 seconds. And then this is 120 and 60. 2, 1, 6, 7. So we have 7,200 seconds here, plus the 900 seconds. That is 8,100 seconds. So you need to be able to convert to be able to get your correct answer. You can now use that value here if you are given a question like that. Now you have to convert 100 gram to kilogram. This is commonly used in the calculation of potential and kinetic energy, where mass may be given as gram, but you are expected to use kilogram. So in that case, if you are given gram, take for instance, you are given 100 gram of mass, and in the formula you are supposed to use kilogram. So what you would do is to divide, that is 1000 gram is equal to 1 kilogram. So 100 gram will be what? 1000 gram, if 1000 gram is equal to 1 kilogram, based on our units, the units of conversion, 100 gram will be what? So that's 1000 times x equals to 100 multiplied by 1. So dividing both sides by 1000, making x subject of formula, we have x as 1/10, which is 0.1 kg. The last one here is 300 centimeter to meter. The relationship here is that 100 centimeter is equal to 1 meter. So if you have 300 centimeter, what would that be? That is 3 meter, or simply use this as m, unknown, then cross multiply. So we have 100 times x equals to 300 times 1. Dividing both sides by 100, you have 3 meter. So I hope with what we've done here, You've been exposed to the importance of measurement and the importance of conversion, then the importance of assigning the correct SI unit to the correct value to avoid confusion. And as a scientist, I believe you will take note of this and be more careful whenever you are carrying out titration, especially whenever you are carrying out any experiment, especially in your titration or chemistry practical. Watch out for the second part of this class, which is on scientific method. And I want to encourage you to treat more past questions, expose yourself to past questions so as to get familiar with most of the questions and avoid practicing in the exam hall. Take care of yourself. Thank you.